Dear learners, let us continue our learning the course Data Structures and Applications. We are in the third session of the module 4. The topics covered under this session are binary trees, different kinds of binary trees, properties of binary trees. Myself, Dr. Suresha.d from the Department of Computer Science and Engineering of Canara Engineering College, Bantwal, Mangaluru. To start with, binary tree. A binary tree is defined as a finite set of nodes such that either T is empty, tree is empty, or tree consists of a root node and two disjoint binary trees called the left subtree and the right subtree. So if you observe the diagram which is present over here, so each node if we take, so either it will have the two children, a maximum of two children are present over here. If I take up the node A, so node A is having the two children B and the C. If we take up the node B, it is having the two children D and the E. If we take the D, it is having the two children H and the I. That is either it will have a 0 children, that is your H, or we can have the two children over there. Fine. So we can have the one children is also possible, but for in complete case there is an type of the binary tree wherein we will study. That is, a binary tree can have either 0 children or it can have 1 children or a maximum of 2 children may be present. We can't have the children more than 2. That is the rule for the binary tree. The binary tree either it is an empty or it can have a maximum of two children. That is, it can have the two disjoint binary trees may be there. So one we call it as the left subtree, which is towards the left side, and the second one we call it as the right subtree. So in this case, A is the root node, B is the left subtree, and C is the right subtree. If you go with the different kinds of binary trees, the first one is a skewed tree. A skewed tree is the one wherein all the elements are present or oriented towards one side. It can be a left side or a right side. The tree arrangement will be like this. So if it is in a left skewed tree, then all its children are oriented towards the left child. That is, if you can see the example, A, B is a child of A, it is a left child of A, C is the left child of B, D is the left child of C. So like this type of a tree, we call it as the skewed tree. So this is a left skewed tree. If you go the right skewed tree, the orientation of the children are present along the right children. All the children will be connected as a right child over there. So this type of a tree, we call it as a skewed tree. The skewness can be either it may be on the left side or it can be on the right side. We can have the left side or the right side. That is, if you go the definition, a skewed tree is a tree skewed to the left or skews to the right, or it is a tree of only left subtree or only right subtree. A tree with only left subtrees are called as the left skewed binary tree, and a tree with only right subtrees is called right skewed binary trees. This is an example for the left skewed binary tree. And the next type of tree is a complete binary tree. So as I told earlier, so in case of a binary tree, the maximum number of children is 2. That is, we have the option of having a one child, 0 child, or one child or the two child. So if I take up the example, the single node is there. So this is an example for your no child. That is, a number of children will be 0. The next will be if I have a single child, that is a, it is having a one child, that is my B. So this will be The A is having the one child over here. The next one will be A will have the two children. Let it be B and the C. B as the left child and the C as the right child. So now A is having the two children over there. So these three options are there for the binary tree. These three options are there for the binary tree. So for a complete binary tree, either it will have 0 children or the 2 children. It will have the 0 children or the 2 children, and a binary tree is said to be complete if all its levels except the last level has the maximum number of nodes will be equal to 2 power of I minus 1. So let me take one simple example over here. Suppose level 1. So level 1 is nothing but your root. So how many nodes may be there? 2 power of 1 minus 1. So 2 power of 1 minus 1 is 2 power of 0, which will be equal to 1 element. That is, we can have the 1 element may be present. For the level 2, it is 2 power of 2 minus 2, 2 minus 1, which will be equal to 2 power of 1, which will be equal to 2. That is, at the level 1, a maximum of 2 nodes are possible. The next one, for the level 3, if we take up, it is 2 power of 3 minus 1, which will be equal to 2 power of 2, which will be equal to 4. That is, at the level 3, we can have a maximum of 4 nodes over there. Fine. And all the orientation will be from left. All the elements will be present from the left to right. So this is how we keep on filling the tree. So such an arrangement we call it as the complete binary tree. Such an arrangement we call it as the complete binary tree. Then next one, full binary tree. So the full binary tree means the levels, the nodes at each level is complete. The nodes at the each level is complete. For the level 1, so if this is my level 1, how many nodes should be there? 2 power of 1 minus 1, which will be equal to 1. The next one, level 2. Level 2 is 2 power of 2 minus 1, which will be equal to 2 power 1, which is equal to 2. Then level 3. For the level 3, it is 2 power of 3 minus 1, which will be equal to 2 power of 2, which will be equal to 4. Then next level 4, 2 power of 4 minus 1, which will be equal to 2 power of 3, which will be equal to 8. So if I total all the elements over there, so it is 8 plus 4 plus 2 plus 1. It is 8 plus 4 is 12, 12 plus 2, 14 plus 1, 15, which will be equal to 2 power of your 4 minus 1. 2 power of 4 minus 1. That is, a complete binary tree will have these many number of nodes. So 2 power 4 is 16. 16 minus 1 is 15. That is, each level, when each level is full, when each level is full, then we say it as a full binary tree. Then we say it as a full binary tree. So this is the third variation of the binary tree. Third variation of the binary tree. The next one is extended binary tree. We also called it as a two trees. A extended binary tree is a transformation of a binary tree into a complete binary tree. So into a complete binary tree. So this transformation consists of replacing every null subtree of the original tree with special nodes. The nodes from the original tree are then the internal nodes, with the special nodes are called as the external nodes. Let us take this example. This is a binary tree because the maximum degree is 2, so this is a binary tree. So in this binary tree, there are some empty locations are there to make it as a complete tree. What are those empty locations? Here we have one blank space. This is to be full, and this is to be full. This is to be full, and this is to be full. Fine. Then next, so such an arrangement. So such an arrangement, if we go, so then next, this should be full. This should be full. Fine. So such an arrangement, we call it as this level. If you take up this level, so this level should be correct. Then this node, if you take up this. Right. So such an arrangement, we call it as a extended binary tree. So that is in case of extended binary tree is a binary tree in which we replace each null subtree of a original tree with the special nodes. So if we don't have any children, we will replace them with the special nodes over there. Those special nodes we call them as the external nodes. Those special nodes we call them as the external nodes, and these are the four different variations of the tree. That is a skewed tree. First one is a skewed tree. That is in the skewed tree. Again, we have the two options are there. One is a left skewed tree. Other one is the right skewed tree. One left skewed tree and the right skewed tree. This is the first option. Then the second one is your complete binary tree. In case of complete binary tree, that is for the to go to the level 4, the elements of the level 3 should be full. To go to the level 5, the elements of the level 4 is to be full. So such an arrangement we call it as the complete binary tree. That is a maximum of 2 power of I minus 1 elements will be present at each level. At each level, that will be your complete binary tree. The next one is full binary tree. The total number of nodes in the full binary tree, it will be equal to 2 power of k minus 1. There is a total number of nodes. That is, it is a full in all respects. That is, for the full binary tree, the total number of nodes in that tree should be equal to 2 power of k minus 1. That is, at each level, all the nodes should be full. That will be your full binary tree. The next one is the extended binary tree, what we have seen earlier. So in case of extended binary tree, we transform the empty, the null subtree with a special nodes. Those nodes we call as the external nodes. And the rest of the nodes we call it the internal nodes. Right? The next one, properties of binary trees. There are two main properties are there for the binary trees. The first one is the maximum number of nodes at level I of the binary tree is 2 power of I minus 1. So to prove this one, so it is a, if you take up a simple binary tree, suppose this is one binary tree with a level of 2. At the level 1, the number of elements will be equal to 2 power of 1 minus 1, which will be equal to 2 power of 0, which is equal to 1. So this is satisfied. At the level 2, which will be equal to 2 power of 2 minus 1, which will be equal to 2 power of 1, which is equal to 2. That is, at the level 2, we have the two elements over there. Right? In the same way, if we continue, is in the same way if we continue at the level I, the number of elements will be equal to 2 power of I minus 1. This is what you need to prove. So this proof will be done with the help of the mathematical induction. In the mathematical induction base is that at the level 1, if I equal to 1, then the number of nodes will be equal to 2 power of I minus 1. I value is 1, 1 minus 1 is 0, 2 power of 0, it is equal to 1. So this is an induction base. The next is the induction hypothesis. So at the level I minus 1, the number of elements will be equal to 2 power of I minus 2. At the level I minus 1, the number of elements will be equal to 2 power of I minus 2. So this is our induction hypothesis. Then next, in the induction step. So in the induction step, what happens when we go to the next level? When we go to the next level, at the level I minus 1, the number of elements will be equal to 2 power of I minus 2. 2 power of I minus 2. Fine. That is by the induction hypothesis. Since each node in a binary tree has a maximum degree of 2. Each node in a binary tree will have a maximum degree of 2. Fine. The maximum number of nodes at the level I is 2 times that of the maximum number of nodes at the level I minus 1. That is, at the level I minus 1, whatever the number of elements we have, to that one we will multiply by a factor of 2 over there. So why we will multiply by a factor of 2? Maximum of each node will have 2 children. That's what the rule of the binary tree. So when we multiply this one with 2 for the next level, what happens? I minus 1 plus 1. That is my next level. So what happens to this one? 2 into I power 2 into 2 power of I minus 2. So which will be equal to 2 into I power of minus 2 plus 1. So which will be equal to 2 power of I minus 1. So this is what our proof is. 2 power of I minus 1. This is what our proof is. That is at the level I, the number of elements will be 2 power of maximum. Maximum number of elements will be 2 power of I minus 1. So this is the proof for the first hypothesis. The first hypothesis says that the maximum number of nodes of level I of a binary tree is equal to 2 power of I minus 1. So this has been done proved with the help of the mathematical induction. Then the next one, lemma 2. So the lemma 2 says that relation between the leaf nodes and the degree 2 nodes, the relation between the leaf nodes and the degree 2 nodes. So whenever we go to the binary tree, we have three different types of degrees: degree 0, degree 1, and the degree 2. So let me write the degree 0 as n0, degree 1 as n1, and the degree 2 as n2. Now we have to prove that for a non-empty binary tree, n0 is the number of leaf nodes and n2 is the number of nodes of degree 2. Then n0 will be equal to n2 plus 1. So let us try to write diagrammatically. Then we will prove this one. So if we go and write diagrammatically over here, if you observe, if you observe here, so first one, the number of degree if we take up. So let me have one more element, one more level I will take up. So this is degree 2. This is degree 2. This will be degree 2. These four are at the degree 0. So how many elements are there in the degree 0? That is n0 will be equal to how many such nodes are there? 4 nodes are there. And how many n2 are there? N2 will be equal to 3 nodes are there. That is n0 will be equal to n2 plus 1. So this is what we need to prove. This is what we need to prove. That is n0 equal to n2 plus 1. So this we have to prove. So this proof will be done in the following steps. You can observe. So as I told earlier, n0 indicates the number of nodes of degree 0. N1 indicates the number of nodes of degree 1. N2 indicates the number of nodes of the degree 2. Fine. So if you take up the total number of nodes, n equal to n0 plus n1 plus n2. Total number of nodes will be equal to n0 plus n1 plus m2 over there. Fine. Then next, how many branches in that tree? The number of branches in that tree and connect it to the number of nodes. If you observe how many branches are nothing but the edges. Edge number 1, edge number 2, edge number 3, edge number 4, edge number 5, edge number 6. So how many nodes we have? 1, 2, 3, 4, 5, 6, 7. That is, if I have 7 nodes, then I should have the 6 edges over there, 6 branches. That is, if I go for equaling this one, if I have n nodes, then it should be equal to number of branches plus 1. If I have n nodes, then it is a number of branches plus 1. That is n equal to b plus 1. So if I go for equalizing this one, so n equal to b plus 1. N equal to b plus 1. Fine. So next, if I go with the b, if I go with the b over there, so b means number of edges. The number of edges will be equal to n1 plus 2n2. So n1 means, let me take the example here. So here, this is a tree. Let me take here. It is a one node. Here it will have the two nodes over here. 2 degrees. Fine. So here, oh, this degree is 2. This degree is 1. This degree is 2. This degree is a 0. 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 Fine. The next one. So that is if you take up the edges 1, 2, 3, 4, 5. So how we can get that one? The number of nodes with the 1. How many nodes there with the degree 1? 1 we have. Then next how many nodes with the degree 2? We have the 2. That is 2 into 2. So which will be equal to 5. That is a B equal to B is your branches. Number of branches will be equal to N1. That is the number of nodes with the degree 1. That is degree 1 means 1 edge is there. That is the meaning. And degree N2 means what? There are 2 edges are there. 2 edges means I need to write multiply by 2. That is a B equal to N1 plus 2N2. If I substitute this one, what is the earlier equation? N equal to N0 plus N1 plus N2. Then the next equation is n equal to b plus 1. B plus 1. So if I substitute for this b, so what I will get? N1 plus 2n2. So this is your n. So now if I leave it and if I do the subtraction here, if I do the subtraction here, so that is a plus 1. This is this plus 1. That's fine. So now it will become minus. If I do the subtraction, n1 gets cancelled, n get cancelled. So this is 0 equal to n0. This is minus 2n2 plus n2. That is minus n2. Then this is minus 1. Then if I equate this one, it will become n0 equal to n2 plus 1. So this is what our proof is. That is n0 will be equal to n2 plus 1. Fine. So this is how we prove. This is how we prove the lemma. That is the number of nodes with the degree 0 will be equal to the number of nodes with the degree 2 plus 1. Number of nodes with the degree 2 plus 1. Fine. So this is the proof for the lemma 2. Fine. You can compare over here. So in the figure B, the n2 will be equal to 4. This is a degree 2, degree 2, degree 2, degree 2. So what is the value of n2? 1, 2, 3, 4. n0 will be equal to how many elements are there? Degree 0, degree 0, degree 0, degree 0, degree 0, degree 0. That is n0 will be equal to n2 plus 1. That is 4 plus 1 which will be equal to 5. 4 plus 1 which will be equal to 5. Fine. So this is how we make the references for this presentation are taken from the textbook Alice Horowitz and Sartaj Sawhney, Fundamentals of Data Structures in C, 2nd edition, Universities Press. Thank you.